Yes.
Ja. Sehr gerne. Ja. I will have a short phone call. I'm sitting there. Genau, das ist Chapter 6, Part 1. So, one of my PhD students will upload it now, and then we'll save, and we can continue the original way. So, guys, who's it, the laser pointer? There's it. Last week and also 2 weeks ago, we discussed sampling, the sampling theorem, and the reconstruction. We started with an analog signal, as it is always the case. And this analog signal should be transferred from the analog world to the digital world. And how can we do this? We have to sample the signal. Yeah? If this is our analog signal and it's a band-limited signal, this is a low-pass signal, then we have this upper frequency limit. We use this Dirac sequence, the Dirac comp, to perform the sampling. The Dirac comp remains a Dirac comp in the frequency domain. As a result of the sampling, the analog signal looks like this. And in the frequency domain, we have this replicas of the original spectrum. If we want to reconstruct from the digital signal, from this signal, the original one, then we have to cut out a region in the frequency domain of our sample signal, and in the majority of cases, we limit this to the baseband and cut out this frequency band here. And this is called the reconstruction. And this week, at the end of chapter 5, we will discuss this reconstruction process a little bit more in detail. And this is the section 5.6, the last section of chapter 5. We have here the sampling procedure, and afterwards, after some signal processing, we want to reconstruct the analog signal from the sample version. And before we discuss this, let us take a closer look to the sampling procedure. Ideal sampling. What's the ideal sampling procedure? What's the ideal procedure to obtain from the analog signal the digitized signal, the time discrete signal, discrete time signal? How can we obtain from the analog signal the discrete time version? Yeah? With the Dirac comp. That's the ideal procedure. In the real world, the Dirac comp does not exist. Ja? Haben Sie es hochgeladen? Hallo? Naja, nur nicht verstehen. Ach, Sie sind. Super. The ideal sampling procedure is based on this Dirac comp, this Dirac pulses. However, in the real world, such Dirac pulses are not possible. And therefore, we have a certain integration over a time interval. This time interval can be a t0, as it is shown here. We integrate over a certain time interval our analog signal. But it's impossible to pick out one value because we always have an integration over a certain time period. And this is here t0. That's the real sampling procedure. And in many cases, we perform a sample and hold procedure where we pick out one value and then this value remains for a certain period of time. Here in this case also t0. And then we go to the next sampling point. And again, the signal remains at this value. What do you think? Why is this important to have this whole procedure for a certain period of time? We think about the conversion of the analog signal to the digital world. Why is it important for us, this whole procedure? Think about the conversion procedure from the analog world to the digital world. If you want to convert an analog signal to a digital signal, we have the sampling, yeah?
Maybe because of the aliasing.
Why? Is it the problem concerning aliasing?
So if the red things is too large, then it would be some overlapping.
Yeah. Not really. That's not really the problem. Yeah. But similarly, in the remote problem, we are really comparing analog to the we think that we are not able to make a we are not able to perform the conversion. Conversion always takes time. Yeah? You cannot convert a signal immediately from the analog world to the digital world. The signal has to remain constant for a certain instant of time because the analog to digital world requires the signal for a certain instant. We need a certain period because only this way we are able to convert the signal. If it's avoided only for one instant, and then it's avoided and then we are not able to convert it. Should remain constant for a certain period of time. But this is the period here. Yeah? So, should be constant. Okay? You understand the problem, the motivation? And if this is possible, this hold, then we can convert it. There is enough time to convert it from the analog world to the digital. Yeah, please.
Understand why it's better to have a longer.
For the reconstruction, it's another reason. But if you think about the sampling, a hold time is always good for the subsequent electronic components.
Yeah, like physically.
Therefore, the electronic components, because you have to charge capacitors, you have to decharge, unload, reload capacitors. And for this time, for this reloading, unloading, recharging, whatever, you need time. Yeah? And you can use this hold period, this hold time to do this. But this is impossible from the electronic point of view. You only pick out one signal and then go back to zero. Yeah? You always need a certain hold period to be able to convert it from the analog world to the digital world.
But we are trying to reduce this whole physics.
In case of the sampling, it's not required because we take this value and then remains constant. Okay? If you take a look here, and we take this value, that remains constant. Take this value, it remains constant, and so on. Okay?
Yeah, but I mean, no, like in today's world, we're not trying to have higher sampling frequencies or smaller amount of holding period and more angular signals to sample the pure.
The sampling frequency is always limited. You cannot go to higher frequencies because of electronic reasons. Yeah, sampling is an electronic procedure, and yeah, it would be better to increase the number of sampling points. In other words, to decrease the sampling interval. More. But it's not possible. We cannot go to gigahertz or whatever. And this hold period is good for the electronic point of view. If we take a look at the next slide, each value is kept until a new value is sampled. This is the best way, and this way is the value is kept only for half of the sampling interval. We obtain gaps. Yeah? This is not the best way, but both are better from the electronic point of view than the direct effects, because we cannot produce this real direct effects. This is the sampling procedure. But from the implementation point of view, this is also quite similar during the step of reconstruction, where we want to obtain from the sampled signal the analog signal again. Also, in this case, we have to deal with the same problem. Are there any further questions concerning sampling? But I think you understand it. This is impossible. Huh? To produce Dirac pulses is impossible. The real sampling would look like this. And if we use a sample and hold sampling, then we will have such stairs here, and the length of the stairs can be different. In this case, we have stairs with the length of the sampling interval, and in this case, on the right-hand side, the stairs are reduced to half the sampling interval. So this would be the ideal sampling procedure. We multiply our input signal in the time domain with the Dirac comp. We discussed this several times. This is the ideal procedure. For reconstruction, this would also be the real and the best procedure to obtain our signal again. We have our Dirac pulses, and then what do we have to do to obtain the analog signal again? If we have this weighted Dirac pulses, yeah, if you think about the reconstruction procedure, einige Folien zurückgehen, schauen wir uns das doch mal an. Yeah, here. The reconstruction procedure, we have here our sampled version, and how can we reconstruct from this sampled version the original signal by carrying out a low-pass filtering. Very simple. Low-pass filtering from this Dirac weighted input signal. Is this a good way? What do you think? Is this a good way in the real world to use this sampled version to reconstruct our analog signal? Why don't you think so? This is a good thing. No, we won't lose information because we are limited to this band. It's not from the information one. What would be another law? From the practical point of view, the Dirac pulse is rather small. Does the Dirac pulse contain lots of energy in the real world? We cannot produce a Dirac pulse, and therefore the Dirac pulse does not contain energy. And if our output signal should contain energy, it's better to replace this Dirac pulse with a staircase function. Now, if you compare this staircase function here, the left one, it's to some extent quite similar to our original signal we want to reconstruct. But it's not equal, but it's already similar. And it contains almost the same energy. In case of Dirac pulses, we would not have the same energy because we are not able to produce infinitely small and weighted with a height of infinity weighted Dirac pulses. We are not able to do this. But we are able to produce such a staircase progress of our signal. Yeah?
Is this why it's better than the one on the right? Because
Yeah.
on the right,
On the right hand side, we will lose energy because of these regions in between that are zero, and on the left for the reconstruction procedure, not for the second, for the reconstruction. On the left hand side, we would have now almost the original signal. So, what does it mean? For the reconstruction, we apply at the output something like this in addition. Now we have a rectangular function, and this rectangular function is multiplied with the sampled version. As a result, we obtain this blue curve, and if we take a look at the frequency spectra, then we have in addition to the information of the signal, this sinc function. And this sinc function refers to this rectangular function from the holds element. Do you understand this sinc function? Yeah, is a result of this rectangular function, and the rectangular function is in time domain, and in frequency domain we have then the sinc function. In the other case, if we switch the domains, if this would be in the frequency domain, then this would be in the time domain. Low pass filter in the time domain is then a sinc function. But now we are here in the time domain, and this is then the result in the frequency domain, the sinc function. So it seems to be very simple, and indeed it's very simple, but we have here a certain problem. What's the problem? We are affecting our original spectrum with this sinc function. In case of a Dirac pulse, this sinc function, no, that's wrong, gets right. Sinc function gets right. Dirac pulse is this rectangular is very small. And the sinc function is right. Then we won't have this problem that our original spectrum from the baseband gets affected by the reconstruction. But from the energy point of view, we have to use the staircase functions because only in this way we are able to produce an output signal with a certain energy. We generate these Dirac pulses in the real world. Do you understand the problem?
No,
No.
I don't understand why you cannot. I mean, what's the energy thing? I don't understand this energy.
Only in our theoretical world, we are able to produce Dirac pulses. And sampling instruction works quite well with Dirac pulses. but we are not able to do this. And for the reconstruction procedure, this would be all fine if you are able to generate Dirac pulses at the output of our digital to analog. That's impossible. Because each pulse has to feature a certain length. Also in the digital world, you cannot reduce. And therefore, we generate the signal with the greatest possible energy, and this is this signal at the output of our digital to analog. And then we obtain the multiplication of the baseband signal, the original signal, with the transfer function of this staircase thing, and the transfer function of the staircase thing is only the multiplication of the rectangular function. And this multiplication with a rectangular function looks like this in the spectrum. With the sinc function. Due to the sinc function, our baseband gets affected. What do we have to do? We only have to correct this sinc function, and then we obtain again our original signal with lots of energy. We'll see it on the next slide. The next slide is illustrated a little bit better. If we take a look at the sampling procedure, once again, we have the sampling, and then we have our hold element, and due to this hold element, the Dirac pulses gets reduced to this staircase function. If we want to reconstruct our signal perfectly, then and we have this Dirac pulses, then it's sufficient to use a simple low-pass filter to cut out the baseband signal. However, due to this hold element, our signal, our spectrum gets affected. This is shown here. And this is due to the frequency response of the hold element. And if we want to reconstruct the signal in the baseband from this signal, we have to correct the effect of the hold element. And we can do this by a smoothing filter. And the smoothing filter is in this case not only a low-pass filter, we have the correction to the addition of the sinc function. In our ideal world, the smoothing filter is only a low-pass, a rectangular function. But in the real world, we have to correct this effects due to the hold element at the output of the digital to analog converter. And this can be done with the smoothing filter. We are here increasing the border, the frequency limits of our low-pass filter. We are increasing the magnitude to compensate for the reduction of this sinc function. That's the reason why it's not sufficient to perform a simple low-pass filtering. No, we have to increase the magnitude at higher frequencies.
So the red one is in time limit.
No. This is in the frequency. This is the filter in the frequency. The low-pass filter, which means for reconstruction. In the ideal world, try to sketch it now. Jetzt schauen wir mal, ob das funktioniert mit dem Stift. Probier es mal wieder. In the real world. Naja, das geht natürlich nicht. Wo ist das? Ah, hier da unten. Stift, schauen wir mal, ob es geht. Ja. In the real world, this will look like this. And due to this sinc function based reduction, we have to compensate here at higher frequencies this reduction. Yeah? And this can be done by increasing the magnitude of this low pass filter. Okay?
Now we know how much this moving is based on the sink then. So if the sink,
Yeah.
so
It's based on the sink. It's based on the duration of the holding. And in our case, in our simple case, we use for this holding the sampling. Then we can put most of the energy in our signal, the output of the digital analog.
so we use the sampling then because there's two time division, right? There's the when the AD goes and then it's like sample and hold, and then there's the hold time, and there's a sampling period, right?
We have to be very careful now because sampling and hold. One refers to the conversion from the analog. Example now, we want to convert the digital signal back to the analog. And in this case, in our ideal world, we have a sequence of weighted Dirac pulses. Digital, weighted Dirac pulses. But these pulses do not contain lots of energy in the real world. That's the reason why we use this hold element also for the conversion of the digital signal to the analog signal. Then the output of our digital analog converter is, in the original case, a staircase function.
Yeah, but I mean the smoothing is based on the hold time.
Yeah, okay. But we have the staircase, and then we want to obtain a flash curve again. Because the staircase function is not like it in the real world. We want to obtain a smooth signal, and in order to obtain the smooth signal, we have to apply a low pass filter, and in this case, a special low pass filter to compensate for the reduction due to the hold element. And the reduction is this sink function. Okay? Did you get it? Yeah, please.
How is increasing the magnitude of the compensation based on
Ideally, we are able to reconstruct the signal exactly with this baseband information which we are interested in. And again, this sink function causes a reduction of our signal in the baseband, especially for higher frequencies. Here. And by this lower filter, this one, the right one, we compensate this reduction of the sink function. We increase the transfer behavior of our low pass filter for higher frequencies. If you take a look again at this red curve, here we increase the transfer behavior of our low pass filter. And this can be performed in the analog world, but we can also do this in the digital world. We can do this for each of those components in the digital world, and then we can use again a conventional low pass filter. It doesn't matter, but we have to be aware of this problem that the whole function, the whole procedure affects the output and consequently the analogs. But please keep this in mind. We use sample and hold elements to convert the signal from the analog world to the digital. But also we use such elements to convert the signal from the digital world to the analog. Pure energy. Okay? Are there any questions? Yeah, please.
You was to say that you said that so you do direct pulses, then
Yeah.
the signal frequency widens, and then you have analyze. But I don't really get it. So you said that if you, what's the, to a direct, then the frequency wavelength, then you'll talk about.
No, because the direct pulse is the frequency domain 1, and direct pulse concerning convolution is the Watt element. Then you can put here in as a transfer function everything at each position you can put there a direct function, a direct pulse, because it's the Watt element. Like multiplication. If you multiply A with 1, it remains A. If you multiply it 10 times with 1, that it remains A. And we can put here transfer functions with a direct pulse, and always we will obtain the same object. Because the direct pulse is the Watt element of convolution. Right? 1 in multiplication. 1 times A is 8. You understand?
Yeah.
Further question? Yeah.
So in the diagram, the output of direct we look at convolution with the step function with the rectangle. Yeah.
This is a rectangular function, and if we have an additional convolution with a direct function, direct pulse, then we will obtain the same object. Because direct pulse convolution with the direct pulse means the same.
Before the rectangle function, still the direct function.
Yeah, exactly. And after, because we have here this ideal sampling. Ideal sampling means for us, we multiply it with the direct pulse in the time domain, and in the frequency domain we have the convolution, but again with the direct function. But we use here this whole element concerning energy. Okay, please. The last question. Yeah. This, we have here the multiplication. The blue line, the staircase, is the result of multiply. Okay. That's okay, but the problem is always the same. We cannot produce an ideal direct pulse. We cannot produce an ideal direct comp. Therefore, we use for digital for the conversion of the analog world to the digital world, hold elements, and also for the conversion from the digital world to the analog world, we also use such hold elements. And we have to compensate it, especially in case of the conversion from the digital world to the analog world. Good. Yeah, that's written here. At the output of the digital to analog converter, there are still high frequency signal elements. Yeah, these are this one. And also in case of the hold procedure, we have this frequency components. We want to get rid. We have to get rid of these components. This can be done by a low pass filter, but due to the effect of the hold element in the baseband, we have to use a special low pass filter, and this is the smoothing filter. And this smoothing filter corrects the damping behavior of the hold element for higher frequency. Okay? Good. The compensation of the baseband signal also can be done in the digital domain. I already mentioned this. The smoothing filter, we can implement it in the analog world, but we can also compensate the digital signal in advance, and then we can use in the analog world the simple low-pass filter. But with this special characteristics here, only a simple low-pass filter is then sufficient. If we correct it in the digital. The compensation of the baseband signal can be omitted if the digital to analog converter works at high frequency. In this case, what happens in this case if we have a high frequency conversion from the digital to the analog world, then our sig function gets right. Yeah. It's very flat. Then we do not affect the baseband anymore. Yeah. The sig function gets right, then we do not affect the baseband. Okay. Yeah.
Yeah, very fast question. I was just wondering, because we're filtering all the time, what about all of the, every time we filter, we also add some phase to the signal, right?
Yeah.
How does this affect, because you're always filtering and so on, and you always add phases, more phases to the signal. So,
Yeah, that's a very good point. We will discuss this after 3 to 4 weeks. The group delay and the phase delay of filters.
okay.
Yeah. In the real world, we always add a certain phase delay, and that's not the problem. But the problem is that the phase delay is frequency dependent. And the group velocity is frequency dependent. And in case of digital finite impulse response filters, we always have the same group velocity and always have the same group delay for each frequency. Consequently, if we have a frequency, an input signal with a certain frequency composition, the signal will be damped. But the phase relations of the components, the frequency components, remain constant. The signal will be scaled, frequency dependent, but the components are not. We do not have frequency dependent. And we call this effect we have a frequency dependent distortion. Distortion. You know it from optics, perhaps from fiber light guides, fiber guides. You have an input signal that very small rectangular mass, then the output will be something doesn't look like a rectangle anymore. This is the effect of distortion. And also in case of filters, we have this dispersion problem. In the analog world, the digital world, we build up FIR filters. There, with such filters, you won't have this problem anymore. But this is a topic. It's fine. Okay. But please keep this in mind, this problem with analog to digital conversion, digital to analog conversion. We always need and use hold elements, sampling and reconstruction. Overall, the last slide for chapter 5, how does it look like? We have our analog signal, our input signal, then we need some anti-aliasing filter to limit our bands. Then we have our analog to digital converter. The analog digital converter can be equipped, or is mostly equipped with some sample and hold element inside. That's part of it. Then we have our processing unit. Signal processing unit. Where in the digital world we can alter our signal, we can filter it, we can amplify it, we can do whatever we want, we can store it, whatever. Yeah? or in the digital world. Mostly, or many times, we want to convert our digital signal back again to analog world, and this can be done with a digital to analog converter. But due to the fact that we have in such a digital to analog converter, oftentimes such a hold procedure, we have to compensate this with this moving filter. And if we have a high sampling rate, also for the digital to analog conversion, this moving filter can be a simple lower filter. But if our sampling rate is rather small, we have to compensate this baseband effects that our components are dense due to the sampling, due to the storage procedure. No? Okay, questions?
This compensation from the DSP.
Yeah, in the digital. You can do this in the digital. Do you have questions? Yeah. Doesn't matter. Okay. Yeah, this is a point, this moving filter, which is oftentimes neglected in lectures concerning signal processing. For me, it's a very important point because, yeah, that's the real world. This moving filter that we have to compensate for such effects, which we have to perform this whole procedure, because otherwise it only works from the theoretical point of view, but not from the practical point of view. Good. Then let us continue with chapter 6. Now it should be possible because the slides have been uploaded by one of my co-workers. Chapter 6. What's the content of chapter 6? Or let us return to this overall content of the lecture. Chapter 2, we studied characteristics of signals. We concentrated on analog signals in chapter 3. Then we discussed LTI systems in chapter 4. Chapter 5, sampling theorem and reconstruction. And the next step, chapter 6, will be discrete time signals in the frequency. We already started with this thing because we discussed the discrete time Fourier transform, and we introduced the discrete Fourier transform. In this chapter, we will use both to describe our signals in the frequency domain. We will start once again with the discrete Fourier transform. From the discrete time Fourier transform, then we will use the DFT, the discrete Fourier transform, as an approximation for the discrete time Fourier transform and for the Fourier transform. The chapter in section 3, this will not be possible today. We will do this in 2 weeks. We will discuss the fast Fourier transform. The idea of the fast Fourier transform, the butterfly structure, how we are able to calculate the Fourier transform in a very efficient way. And then windowing and spectral analysis for stationary and non-stationary signals. What is the motivation? Why do we perform the Fourier transform and find this discrete time Fourier transform, the discrete Fourier transform? Why do we use the Fourier transform for many applications? We discussed several reasons for performing the Fourier transform. Do you remember some reasons? What is used, where it is good to perform the Fourier transform? Exactly. Figure out which parts of the biology. Exactly. That's an application to get. We can say to obtain information about the frequency content of groups. We are interested in the frequency content of our signal. we carry out the Fourier transform. This is also useful. You have to calculate the convolution of signals. Yeah, you can do this in the frequency domain because in case of convolutions, the frequency domain, we can handle this with multiplications. It's a great advantage. Here, some further motivations. Numerical calculation of the spectrum, which means of the frequency content. We do this for the calculation of the spectrum of the communication signal. If we have to perform a vibration analysis of mechanical structure, we calculate, we take a look at the frequency spectrum, but also we are interested in overtones of our nonlinear amplifiers. If we search for sine signals in noise, yeah, then we always perform Fourier transform. And in our case, we perform the discrete version of the Fourier transform. We can use the Fourier transform for the calculation of the convolution. We can also use it for the calculation of the correlation. This will be a topic of chapter 9. And the DFT, the discrete Fourier transform, can be very efficiently calculated by means of the fast Fourier transform. So, on this slide, a short repetition of the formulas from the last chapters. We have here the basic definition of the Fourier transform and the inverse Fourier transform. Fourier series, which leads to a line spectrum for a periodic signal. And here we can calculate from the Fourier series coefficients our original signal again. And here on the last line, the definition of the discrete time Fourier transform. And the discrete time Fourier transform leads to which kind of spectrum? Is the spectrum discrete or is it continuous? It is continuous, exactly. The discrete time Fourier transform leads to a continuous spectrum. So, and last week we already discussed this. The discrete Fourier transform leads to a discrete spectrum. This is the discrete time Fourier transform is the starting point of the discrete Fourier transform. And the main difference between the discrete time Fourier transform and the discrete Fourier transform is the fact that in the discrete Fourier transform we also discretize the frequency domain. This is shown here, how we can write this down in a very compact manner. We can say, yeah, we do not use now as starting point the discrete time Fourier transform. Now we use the Fourier series as starting point, because in the case of the Fourier series, we have discretized frequencies. Fourier series is based on discretized frequencies. The harmonic, the first harmonics, the second harmonic, the overtones, and so on. But it's given for a line spectrum, and line spectrum means we have a discretized frequency spectrum. And therefore, we can use the Fourier series as starting point to deduce, to derive the discrete Fourier transform. And this is shown here. We have here our Fourier series, and we introduce the time period t. Uppercase T is n times Ts. Ts is the sampling time, and n is the number of sampling points. Then we can calculate the Fourier coefficients of our Fourier series, Ck, can be calculated in this manner. That's the formula which we already discussed for the Fourier series several weeks ago. Very simple formula. We discussed it with cosine and sine, but we can also write it down with the exponential function. And then we insert, instead of this time, the number of sampling points and the sampling period here. The remaining part, the other parts remain as has been here on the left hand side. And then we insert, instead of this signal in the continuous world, the signal in the sampled signal. Yeah? X from T is the analog signal, and now we replace it with the sampled version. This can be done, but it's very important that this is not completely the same. It's an approximation. It's an approximation because we are not thinking about band limitations and so on. We are only saying, yeah, we replace our continuous signal with sampling. This is done here. The sampling points to obtain a time information, we multiply it with this derivative. And then we have again the integration, but here the summation. Due to the linearity of both procedures, integration and the summation, we can change the order, and we can say that in one during one sampling period, one sampling interval, the signal remains the same. That's the idea of sampling. And therefore, we can replace this integration by a multiplication with ds. Okay? Very simple. Remains the same during the sampling interval, our input signal, and therefore we can multiply it with the sampling interval by itself instead of performing an integration. Yeah, and then we're almost at, we almost reached our formula for the discrete Fourier transform and the inverse discrete Fourier transform, because this formula we can cancel out this n times ds, or ds can be cancelled out in this case because we have it here and here, and also this ds can be cancelled out with this one. And this is then the resulting formula, and this is indeed the definition of the discrete Fourier transform, and here we have the definition of the inverse discrete Fourier transform. What's the difference between this formula and this formula? Yeah, the Fourier series coefficients, there we have to multiply them with n, the number of sample points, and then we obtain the discrete Fourier transform from the Fourier series coefficient. If you compare this formula with this one, the only difference is n. Yeah.
What question about the information from
Yeah, because very good point. I didn't mention this because in this case here we are considering that our signal we start counting our signal with the index 0. Yeah? Xn is our first point of the signal, or in other words, we assume a causal signal which starts at 0. But you can also consider signals for negative times. It's not a problem. Because we are now in the world of index and not of time. It's an index, and a signal with a negative index, it's not very good because from the filter world, we start with index 0, or we start with the talk of negative index values. Yeah, but this from here to here, it's only an index. It doesn't matter for us to start with index 0 or with index minus infinite, because negative index in the computer doesn't exist. Okay? Think about okay, now I understand the problem. Yeah, now I understand it's already. excuse me. Your problem was, why do we have here this infinite and here we have the period? Okay, I'm very sorry. That's sufficient for us because we assume a periodic signal. The signal gets repeated. Therefore, it's sufficient to consider only one period. And this is the period from 0 to n minus 1, because it's one period consists of n centimeters. Okay. Also, this thing from my side.
If it's not, you cannot.
If it is not periodic, then we cannot use the DFT in our original definition. Because if you remember the last week, in case of the DFT, discrete Fourier transform, we always have to assume that our signal features some periodic behavior. We limit we only take a look at the signal for a limited amount of time, and outside this time, we assume that the signal gets repeated periodically. Only in doing so, we are able to obtain a frequency discrete spectrum. Otherwise, our spectrum will be good. Discrete Fourier transform, inverse discrete Fourier transform, lowercase xn and uppercase x from K form a transform couple. Here we are in the time domain, or in the original domain. Here we are in the frequency domain. We call it also the image domain, because it's the image of our original signal in another domain. If lowercase xn is given, the frequency domain can be calculated using the discrete Fourier transform. And if we have the signal, if we have the signal from the, if we start with the signal in the frequency domain, then we can calculate the original signal by using the inverse discrete Fourier transform. Some further points. This is very important. The spectrum is in general a complex number. This means it consists of a real part and an imaginary part. But we always sketch the magnitude, and in the magnitude we have both parts included. We can visualize the real part, the imaginary part, but we can also visualize the space. It's completely the same. We call this index m the time index or sample index. The index, this parameter k here for the frequency domain, is the discrete frequency variable. The sequence of the DFT coefficients is periodic with the period n, and this is valid for the time domain and the frequency domain. Our signal is then periodic in the time domain, and also the spectrum that's repeated periodically. Periodic signal in the time domain, the periodic signal in the frequency. Okay? Good. And only in this way we have sample versions. Therefore it's sufficient to calculate this for one period. We can limit this summation from 0 to n minus 1. We do not have to consider the whole signal because it's repeated periodically. After the inverse transform, the sequence can be interpreted as a periodic signal with the period n. The basic period matches. I think all these things written down here, they are very easy to understand. Let us talk about the step size, the sampling distance. It's given by if we consider the sampling, the length of our entire signal, then we can calculate from this length of the entire signal the distance between two sampling points in the frequency. Okay. I have a signal which reaches a length of 10 milliseconds, and the distance of sampling points would be 100 hertz. That's the distance between two subsequent points in the frequency. 100 hertz. But the upper frequency limit in the frequency domain, it's given by the number of sampling points and the time window we consider. If you consider this time window 100 milliseconds, then the distance between 2 points in the frequency domain will be, did I mention 10 milliseconds or 100 milliseconds? 10. Then we have here 100 hertz, and if we use 100 points in this 10 milliseconds. I think I should write it down. 10 milliseconds. 10, yeah, not 100. Then the problem with the zero tokens. Yeah? Okay, let us assume that our sampling, our considered duration of the signal is 10 milliseconds. Then we assume in this 10 milliseconds 100 points. Yeah? Points. Exactly. What's the difference between two sampling points in our frequency domain? This is Fs. The frequency domain of our signal is then 100 hertz, exactly. And the upper frequency limit, we call it lowercase fs, or it's also called uppercase fs here. No, it's this f signal length in the frequency domain without the what's this? F is then here. What's the upper frequency limit? 10. What? 10? 1? 1 kilohertz. 10 kilohertz. Who is trusting your colleague? Are they alle? Yeah? Ah, yeah, 10 kilohertz. Okay, then I write it down and we will discuss it. This is the correct solution. We have here 100 points, and the sampling is here. The difference is 100 kilohertz. 100 times 100 is 10 kilohertz. Seems to be correct. Exactly. So, and are there further parameters? No, I think we have calculated all the parameters. Are there questions? And if you study your signals with MATLAB, you always have to do this by yourself. You have to calculate all these values by yourself. And most guys have problems in calculating these values. And if you ask colleagues about this difference, they are not able to calculate this difference of two frequency points, this frequency interval. One point is still one value we didn't calculate up to now. What's the sampling time? The time interval between two subsequent points in the time domain. Exactly, 100 microseconds, because it's a result of the 10 kilohertz. Yeah. The time domain, we have the time, and this is the time signal. We would have here our sampling points in the time signal. And this is the difference between two sampling points is our TS, and the final value, the considered time window, is T. And if you take a look at both figures, you can see that it's the same in the time domain and in the frequency domain. Therefore, the discrete Fourier transform is only the same. It is the discretized version of the discrete time Fourier transform, because we have discretization in the frequency domain and in the time domain. Questions? Very simple, but this could be also a topic for the written exam to calculate such values. So, good. Then let us continue. This formula, both formulas are very important, and they are written here again. We have here the direct, the discrete Fourier transform, and here the inverse one. And the interesting part is, if you take a look at the transform kernel, in both cases we have this exponential function. And we can write this in a compact manner. We can use this exponential function as a phasor and write it in this manner. Here we have the parts of the exponential function with the argument minus j2 pi divided by. And if we use this so-called rotation phasor, then we can rewrite both formulas, the direct transform and the inverse transform. So, why is it called a rotation phasor? There's an angle. Yeah, because it's the complex part. If we have an exponential function with the arguments containing j, then it's something like a rotating pointer, and in this case we call this rotating pointer rotating phasor. It will be rotating this manner because we discretize the rotation. And for the continuous Fourier transform, it rotates periodically in a continuous way. Each position is possible, but in case of the discrete Fourier transform, this position, depends on the discretization of our frequency. But we always have to deal with the discretized angle. Discretize our 360 degree by the right number of steps. And if we now use this phasor, we can write this in a compact manner. And it's very interesting that in both cases we can use the same phasor. In the first case, due to this minus sign here, we can use here a positive sign. And for the inverse transform, we have to consider this minus sign, and therefore we have to use here in addition a minus sign. Minus times minus gives again plus, and therefore we obtain this formula here again. Here we have the positive phasor, and here we have the negative phasor. Questions? On the next slide, you will see that this makes sense if you listen this way. Because you can implement this step in it's a math system.
The magnitude of that phasor is always 1, right? In the WN, so then just make it the x and
exponential function with the argument j times something leads to a okay. No further questions? Good. We have here the discrete Fourier transform and the inverse version. And now we use, instead of our signal sequences, vectors. We use the vectors bold x, lowercase x from n, and here bold uppercase x from n. This are the vectors. And we can also put our rotation phasors in a matrix manner, and then we can write down the DFT as a simple matrix multiplication. And if you think about an implementation of a computer system, the multiplication of a vector in a matrix is always fun. That's the reason why we introduce this phasors, because then we can write it down as a matrix multiplication. The summation is done by the multiplication of here we have the multiplication of this line with, for instance, this one. Then we always have, from your side, we have always this procedure that we multiply in this manner and we sum it up. And this summation is required due to this summation here. Therefore, we can simply write this down. The discrete Fourier transform is a matrix vector multiplication. And this works for the direct discrete Fourier transform, but it also works for the inverse discrete Fourier transform. The only difference is this W. In case of the inverse Fourier transform, we have to use the inverse of this matrix containing the rotation phasors. And yeah, you can show due to the fact that the rotation phasors consists of real numbers and imaginary numbers. We have the exponential function with the argument j times anything. Then we have the real part and the imaginary part. The inverse is only the complex conjugated version of the original. Are there any questions? This procedure will be adopted in the exercises too. We will use this to calculate the discrete Fourier transform. You will have to calculate the discrete Fourier transform of simple signals in the written exam. We will discuss this with co-workers in the exercises. This procedure with the matrix vector multiplication. It's very important that you are able to write this down and mistakes during the calculations. But MATLAB, if you calculate the discrete Fourier transform, MATLAB will use exactly this procedure. We only evaluate the multiplication of the matrix containing the rotation phasors with the vectors. Questions? No. Then let us discuss some examples on. Das ist, kommen wir ein bisschen später. Bevor wir noch das. Yeah, this we already discussed. We can imagine that this rotation phasor is a pointer, and the pointer, we have defined positions of this rotation phasor, depending on the discretization of the frequency axis. And discretization of the frequency axis is here performed by uppercase n, but it also refers to the discretization of the time axis. Discrete Fourier transform means we have a discretized version of the time axis and the frequency. The discretization of both is uppercase n. And therefore, this refers to the frequency domain, but also to the time. And here we have this one which you asked. The length is always 1. Discretization, the period n. and the time domain and the frequency domain. Here it is shown for the example that we have 8 discretization points, and yeah, it's not completely symmetrical. Yeah, but you can imagine it. It should be a circle with 8 elements. Yeah. Good. An interesting point at this part is if we have here 0. What happens if we have 0? If we multiply our phasor in the argument of the exponential function with 0, then the phasor will always be 0 in the argument, and therefore we sum up all phasors in this sum. And what's the result? It's a phasor of the length n, because the length for the position 0 is always 1. It's a real number 1. We sum here all these phasors up. And in the other case, due to the summation and this argument, we always switch with our phasor. And now a very important part. If you have a sinusoidal signal, then you will obtain from your discrete Fourier transform the frequency of the sinusoidal signal. Discretized sinusoidal signal. We assume that this is a discretized sinusoidal signal. Then we will obtain exactly, if you do all the things in a correct manner, we obtain exactly the frequency of this sinusoidal signal. Why do we not obtain other frequencies for a signal which is correctly sampled as an output of the Fourier discrete Fourier transform? If we assume a sinusoidal signal with a frequency of 50 Hz, we assume that the signal is correctly sampled. We use the correct sufficient sampling periods. All the things are correct. Then we will obtain a result of the discrete Fourier transform 50 Hz. Why would we not obtain 25 Hz, 30 Hz, or whatever? We have an idea why this is.
What's the question?
Yeah.
Also, the purity system?
If it doesn't depend on the values.
Oh.
If we have a sinusoidal signal, again I mentioned 50 Hz. Let us assume our sinusoidal signal has 50 Hz. Then our discrete Fourier transform will provide a frequency spectrum with a component at 50 Hz. Why will we not obtain a frequency signal at 60 Hz or 40 Hz? We have an idea, yeah?
You get the clear transfer in the sample domain, say sample and processor.
Yeah, I think the question is really hard to answer because due to this fact here, it's really hard to answer for you because I think it's hard to imagine. Our sinusoidal signal is rotating in the frequency domain if we consider it as a complex signal in this manner. Yeah? Our transformation, the phasor, is rotating in the opposite manner. You understand? I think I need to. Yeah. Yeah. I tried from. That's difficult for me because I have to change the angle. So the sinusoidal signal is rotating in this manner, in the complex domain. Yeah? This should be the original signal. It's rotating in this manner. Our rotation phasor is rotating in the opposite manner. And what's the result if we multiply two phasors rotating in the opposite manner? a real number. And the real numbers are summed up for each position of the rotation phasors of both. We have discretized version. This is the starting one, then we are so, this, so, and so on. And the results are numbers pointing always in the same direction. And if our rotation phasor is rotating with a different velocity, angular velocity than our signal, then the sum will cancel out and the result will be zero. You understand?
I mean, I just don't get why do the multiplication of the two vectors or the two, let's say, phasors would be scalar and not a complex number.
If you, yeah, I will write it down. This is a very good question. If we have two phasors, the phasor and the signal, and both have the same frequency, then we can say one has the amplitude 1 and the phase +5. And the phasor is rotating in the opposite direction. Then we have here 1, or let us assume this is the amplitude is A. And here we have as amplitude 1, but minus j omega, j phi. And the result is then A with 2. Okay?
And this only will be the case then.
If we have exactly the correct frequency. Otherwise, the sum will be 0. This is also a part in discrete Fourier transform, which is most of the lectures do not mention it. This, the lectures do not mention this, but in my mind, so for me it's really easy to understand the Fourier transform. Think about this fact. You have this in mind that the rotation tensor is rotating in the opposite direction as our signal. And only if both frequencies are equal, then we will sum up the scalar products of both in a perfect manner. Otherwise, the product will be the sum of the products will be 0. Okay? You understand?
No.
You also understand?
No, I think we need more time to write down.
Can I maybe that's all this question now?
Yeah.
So the thing is that so they're saying that the sampling of the phasor is the same as our signal, right?
Yeah.
But then this is not according to Nyquist. Like you have to always send it twice faster, at least double the frequency than your signal, right?
No. No. That's written. Ist hier ein Schirm dabei? Das wird schon auf. The point concerning sample. The phasor, if we have the sinusoidal signals, yeah, and we do not fulfill the Nyquist criterion, then our phasor will move more than once concerning the sampling. Yeah? In the case of Nyquist, we have two sampling points of our phasor. This one, this one. Otherwise, we are not able to sample.
Yeah.
But if we fulfill this, then it works. Nyquist, one point, or one sampling point in this direction, and another one in the opposite direction. Good. Now, okay. You have to think about this fact managed by yourself. But for me, it's very good to imagine the point of the Fourier transform. And this is also shown on this slide here. Yeah. The discrete Fourier transform it rotates your original signal back to the real axis. You have a rotation of your signal, and by the multiplication with the rotation phasor rotating in the opposite direction, you multiply, you project it to the real axis. To the imaginary axis can also be if you have an additional phase, but to a constant value. And this is shown here. We have here our phasor or our signal in the complex domain. We have the real part, the imaginary part, and here we have the time. Our phasor and our signal rotates with respect to time. And by means of the discrete Fourier transform, and also it's the same for the other transforms, yeah, for the Fourier transform, but in case of the discrete Fourier transform, it's easier to imagine because we have only discretized versions of our phasor positions, yeah. Example in the frequency domain. We multiply it, sum it up, and due to this multiplication and summation, we get rid of the rotation of our signal. And the rotation will be cancelled out. As I have written down it here. The result does not rotate anymore. In other words, the Fourier transform de-oscillates your signal. You multiply your signal with the phasor, and the phasor de-oscillates the signal. The originally oscillating signal is converted to the baseband to a constant value by de-oscillating. It's another explanation of the Fourier effect. And also, this also discrete Fourier transform, discrete Fourier transform, it's always the same. The de-oscillate your signal. Get rid of the oscillations. Okay?
Yeah, I just don't want to. But yeah, the thing is that the discrete will always